Hi everyone. This week we're going to have another Python lecture, and our micro lecture is going to be about cloud computing. We have a few announcements before we go ahead and get started. The first thing is we have an event.
I'm Matt, I'm with Founders. Quick overview of Founders in general is that we're the Student Entrepreneurship Club, and we give money and support to any student startups on campus. Student startup isn't really a startup most of the time, it's just like a project that you decide to call a startup. So, pitching to this class, I try to do it at least once a semester, because I know that I had a really cool project when I was in here, and I'm sure someone around here would like an extra $300 to keep doing it. So, more specifically, I'm here today about Genesis, which is co-hosted by Founders and Jump Capital, Jump Trading, and Jump Labs. And so they're a VC firm focused on fintech applications. I'm sure all of you are in the circles where you start hearing blockchain quite a lot. So Jump Genesis is a startup weekend focused on blockchain applications, mostly applications built on blockchains, but anything goes. If you want to make a new protocol, go for it. We're not really focused on getting a product finished by the end. That might help with the judges, but it's not required. You come in, form teams on Friday after everyone pitches their ideas, sort of like a hackathon does, and then on Saturday we'll have mentors from the industry, some from Chicago. Some of them have started their own crypto companies. Some of them are just lawyers around who can help with IP issues, stuff like that. We also have a panel from some fintech execs from Chicago. That'll be at 1 o'clock Saturday, free to come. And then Sunday is the judging. Prizes are up to $2,000 in grants, no strings attached. Connections from founders if you decide to continue with it afterwards. And then you can get an interview with Jump Capital as well. There's going to be free food, free swag, and it's like very low time commitment. You don't need to stay the entire weekend, like at all. And you also don't need to know anything about blockchain. The average student startup ends up being about 1 year, and if you're thinking about starting your own company in the future at any point in time, I would recommend going to this event or any one of the ones that Founders puts on. So, does anyone have any questions? Well, thanks, hopefully I'll see you there.
Okay, so let's go ahead and do the attendance quiz now. Okay, is everybody done with that? All right. Okay, let's go ahead and move on then. Okay, homework 6. There's no information on the slide, but there will be a homework 6 released either very late today or tomorrow. We'll post the deadline on Piazza, but it'll most likely be due next Tuesday at midnight, same as always. So yeah, keep that in mind, and it's going to cover the Python that we're going to go over today. Okay, once again, we have office hours these days, these times. If you need help, make sure to come in. Okay, and then a note about final presentations. So it's good to know when these are, so you can start planning what you need to finish up before the end of the semester. So final presentations are going to be on May 1st, which is the Tuesday before reading day. So that's 3 weeks from now. So you have plenty of time to finish up whatever needs to be done in your project. It's going to be from 7 to 9, and we're going to do it in a kind of science fair style. So if you happen to see the presentations last year, we had tables set up in the atrium, and we basically just had people like demo their projects, and then a lot of people walked around and could see what was going on, and that's how we graded them too. So we walked around and took notes on the projects. So it should be pretty fun. There's 10 projects this time. Last time we had, I think, almost 30, so it's going to be quite different, but it should still be a lot of fun. And we're going to try to get other people to show up, people who aren't in the class, to come see your projects. We're going to have food, so hopefully that'll get people to come out and look at things. So all your projects are super cool, so people should be interested in seeing what you guys are doing. Okay, so let's get started with Python, and then after Python, we'll have our micro lecture, which is going to cover cloud computing. Okay, so today we're going to be covering recursion. So does anybody know, can anybody give me a definition of what recursion is? Yeah, back there.
It's when you have a function call itself and keep calling itself until it eventually reaches the base case.
Yeah, that's a good description. So ideally, that's what we want to happen, right? So we keep calling a function over and over again, and it reaches a base case. And so some bad things happen if we don't have a base case, and we'll talk about that. But that's a good definition. Okay, so you can see here the definition we have up here. Recursion is when there's repetition. So basically, you have some sort of problem, and you can break it down into a subproblem that's almost identical, and then keep doing that. And so the way you solve the problem is by calling the same function again and again until you get to what is called the base case. So the smallest thing, or the point where you're at the end. And that can be a little bit confusing, but we'll go over what that means. Okay, so here's an example right here. So what we're doing here is, you can see we have import time, so we're doing stuff with time, and all we're doing with that is basically just making the function pause, right? So that's pretty straightforward. And you can see here what the function does is just, it prints hello recursion, right? And then it returns the function itself, right? So let's take a moment and think about that for a second. So all the functions you guys have written up to this point have been like a function, definition, function, and then you do a bunch of stuff, and then you return, right? But in this case, it's really different, right? Because we do some stuff, and then we call the function itself. So basically, you're going to go through this. So if I call hello recursion, we go through this, we say time.sleep, we print this, and then we say return this. And when we say that, we call the function again, right? And so then it goes and it says, oh, time.sleep 0.5, it prints this, and then it returns the same function, right? So then it calls this again. So it's just a function that's calling itself over and over, right? And so this is pretty interesting, right? So basically, as was just pointed out, if you want to stop the recursion, you need a base case, right? So you need to stop at some point. So this one is problematic. Can anybody tell me why? Yeah, back there. Exactly, it has no base case. So what it's going to do is just keep calling itself, right? So it's just going to call itself over and over again, but there's nothing here that says stop, right? So that's an issue. Does everybody get that? So if you've never seen recursion before, or it's a little new to you, this is probably super confusing. Because I remember this was super confusing to me when I first learned about it. So does anybody have any questions? Okay, so let's go ahead and let's see how this works. Okay, so we're gonna run this. Somebody tell me what you think is gonna happen. Someone on this side. We haven't had anybody answer on this side. Yeah.
The function is going to repeat itself so there should be a hello recursion print every 0.5 seconds.
Exactly. So what's going to happen is it's just going to keep doing that over and over. So I'm running this. See what's happening? And it's never ever going to stop, right? So it's just going to keep going forever and ever. So I actually have to stop this. Because it's just going to go forever, right? And if you're running a program and you have something like that, you're going to get what's called a stack overflow, because every time you call a function, it allocates memory on the stack. And so if you do that too many times, you just run out of space. So when you guys get to like 225, if you're planning on doing that, you'll learn about that, and it'll be super annoying, and you'll get some nice experience trying to fix those problems. So yeah, so you can see when we don't have a base case and the function is called over and over again, it never stops, right? Because nothing here is saying stop or return from this function. It just keeps calling itself. Okay, so let's take a look here. Okay, so now we're going to talk about base cases, right? So this is saying we ran this and we're stopped. We need a base case to tell it when to stop, right? So in this particular function, can somebody tell me, somebody just give me an idea of what this is doing this time? Let's get somebody in the back row on the left side.
So it's every time you recurse through the function, it's decrementing n. So if you start with some n value like 5, it'll go until it'll decrement n until n is stopped once n is less than 12.
Yeah, exactly, right? So what's happening here is this is our base case, right? So we have this condition that says if n is less than or equal to 0, then we print this, right? We say, hey, we're at the base case, right? And then we return. And then otherwise, we print hello recursion, right? With n, and then we return the function. But the parameter in this function is n, right? And every time we call the function now, we're decrementing n. So eventually, we're going to get to a function call where n is less than or equal to 0, right? And then we're going to reach this case. So this can be a little bit difficult to visualize what's going on. If you guys, if you're in 125, have you gotten to recursion yet? Yep, okay, so you know about activation diagrams and whatnot, right? Maybe not yet. Okay, so we're going to talk about that. So if you haven't seen recursion at all, this might be a little bit tricky. But hopefully being able to visualize it will help. So you can see, this is very straightforward. So we call, so we just keep calling this until we get to n equals 0, and then we're going to stop. And then basically what happens is, so this returns, right? So we call the function, let's say, here it's 10, right? N is 10. So we call the function, and we say, okay, well, n is not less than or equal to 0, right? It's 10. So we print this, and then we call this on hello recursion 10 minus 1, 9, right? And so then we keep doing that until we get to the very last one, right? So we do this, and then we can finally return. And then we'll return here to where we called the function when n was 0, right? And then we'll return to the function call before that, where n was 1, and then where n was 2, and we just keep returning and returning until we get to where this original function was called. So let's go ahead and let's see what happens when we actually run that. Okay, so you can see here, it printed it out 11 times, right? So, makes sense, right? So does anybody have any questions about this? Don't be afraid to ask, because I feel like this is confusing, and a lot of people are probably confused. So does everybody get how this works? Okay, so let's move on and let's kind of try to visualize what exactly is happening. So we can use something called a visualization diagram, and this is like a really good way to figure out where exactly you're going in your function. So when your function calls itself, you basically make like a little node or like a little circle, depending on how you're doing this. I'll show you an example in a second, but and you can see each circle in our activation diagram, or each like step, is going to represent a function call, right? So basically what this helps us see is how exactly we get to the base case and then how we return up to the original function call. So let's take a look at this. Okay, so this is a visualization. This is an activation diagram for the one we just did, right? So we can see here we started with n equal to 10, right? And then it called the function with n minus 1, right? So then it was called on 9, right? And then it did that again. It was called on 8, and it's not reaching the base case yet, right? Because we haven't hit 0. So it keeps calling itself, and each time it's decrementing n, right? So it's going lower and lower and lower, and we keep going, and then we get 0, right? And so what I like to see with this, and what's not here, but what I would have added is, once you get to this base case, right, it's like we've just gone through a bunch of functions, right? A bunch of function calls. So you can see here, like this one called, so 10 called it on 9, and then on 8, and then on 7, and we're just getting deeper and deeper, right? We keep calling the function again and again, right? But the important thing is that once we reach the base case, we have to come back because we originally called the function on n equals 10, right? And so what we need to do now is return from all of this. So when we get to the base case, when you saw the code here, it says return, right? So we're going to return up to the next function call, right? The one that we called before it, which was right here. And then we return again to the one before that. So what I like to see with these is little arrows that come back, right? So instead of this just going this way, when we get down to the base case, we have a return that goes back up to here, and then back up to here, and here, and here, and it keeps going until we get back up to here, because this was the original function call. And that's where we get the final return, right? Okay, so does that make sense to everybody? Does everybody get how activation diagrams work? Or if I gave you like a recursive algorithm, you could draw an activation diagram if it was something simple. Does anybody have any questions? Okay. So yeah, so this can be a bit confusing. I recommend, like, if you're doing the homework, you don't understand, just draw an activation diagram and just really, really think about what exactly is happening, right? So it can be very, very confusing if you try to think about everything at once. So you can either draw the activation diagram. So like when you're first learning, draw the activation diagram and see how it actually goes through and how it does each step. And then once you understand that, you're going to get really good at doing recursion without thinking through all the steps. So you basically learn how to do it by just putting your faith in the fact that if you do the first step right and you have a base case, all the intermediate steps are going to work out. And that's when you know, like, you really understand what's going on. Okay. So let's see here. Yeah, so this pretty much summarizes what we were talking about. So with the recursive algorithm, our goal is to solve subproblems that are similar to the original problem we wanted to solve, right? So let's say we can run a recursive algorithm on a array, right, or a list, and then maybe each time we pass in a smaller portion of the list, but the algorithm, like the actual code, does the same thing to that portion. It's just being run on a smaller and smaller piece, right? So there's so many recursive algorithms out there. Like if you want examples, you can find so many, and you'll understand what this means. Basically, you just want to get it to be smaller and smaller until you reach the base case, and then you can return up through all your function calls. And then identifying the base cases are super important, and usually I'd say that's the easiest part, is just saying, you know, what is the smallest, it says here, like, what is the smallest possible problem? What is the last thing we have to solve before we can come back and return through all the function calls? Because we usually need that base case value to do stuff with, so we can come back. And we might do like computations along the way as we return through the function calls. Okay, does anybody have any questions about that? Okay, it's okay to be confused. I think once you work through the homework, you'll understand it a bit better. Okay, so let's take a look at this example. So we've got, everybody knows what Fibonacci numbers are, right? That's pretty simple, right? Okay, so you guys did Fibonacci before, but you weren't allowed to use recursion. So if you're kind of advanced and you're like, oh, I'm going to use recursion to do this, we didn't let you, right? Because it's super easy then. So let's look at this code and let's think about why. So we have this recursive Fibonacci algorithm here, right? So we've got two base cases, right? So this goes along with just Fibonacci numbers in general, right? If you were going to write them out, this is how you would think about it, right? So if n is less than 0, we have 0, and then if n is 1, we have 1, right? But then otherwise, we have to base, once we have those two numbers, we have to go ahead and create the rest of them, right? But we need those two to go ahead and do these. So basically, if you want, this algorithm is like, if you want n Fibonacci numbers, it'll go ahead and generate those, right? So let's go ahead and see what's going on here. So let's see. So you have your two base cases here, and then you have here, this makes sense, right? So you guys have been in math classes. You know that, like, you know how Fibonacci series works, right? So here we have n minus 1. It relies on the previous value, and this is n minus 2, right? So let's go ahead and let's run an example of this. Okay, so let's call this on, okay. All right, there we go. So, yeah. So basically, what this does, like, you can see, like, this is what the above paragraph was talking about, is that breaking it into smaller and smaller problems until you get to the base case. So when you have, you know that the numbers start with like 0 and then 1, and then you have to build off of those, right? So we know that, like, here we have these two, right? And that's going to break the problem down smaller and smaller, right? Because every time n is going to be decreased, right? Either by 1 or by 2. So there's actually 2 recursive calls here, right? And then the end, we just add them together, right? Okay, so that's just a very simple example of how it works. If you don't understand, I recommend that you, like, draw the activation diagram. It'll be pretty simple, and it's good to get a really, really good understanding of this. You don't want to be like, I kind of understand how recursion works. You want to be like, I really, really understand how this works, and I can write these kind of this kind of code. So yeah, so basically, in summary, you make a smaller and smaller problem until it's something that we actually know how to do, right? So here we've got, we know this is the general formula, right? And then we keep going until we know that we get 0 and 1, right? And that's our base case. Okay, so let's see. Yeah, so when you talk about activation diagrams, they can look kind of different, right? So for this one, it's going to look something like a tree. And so you guys can take the time to go through and draw that and just see, like, you can see what it's going to look like. Because here it makes 2 recursive calls every function. So yeah, so you can think about what that's going to be. Okay, so now we've got another example. So basically, you've seen recursion used for things that are, like, intuitively recursive. Now we're going to see something that's a little bit different. So with this one, we are going to sum the list, but we're going to do it recursively this time. So you guys would know how to do this iteratively, but this time we're going to change it up a bit. So let's see. Okay. So basically what we need to do is we need to take the main problem and then split it up into smaller problems, right? So let's take a look here. So we've got a definition sum, and we put in I, right? And then here we add the value at I with sum I minus 1, right? So we're just going through the list and we're summing it, right? Okay, so yeah, and then let's see. So we modified that a bit because we didn't actually define list yet, right? So let's see. So in the end, we get something like this, right? So we actually have to pass in a list, right? Because list was not defined. So we had no clue what we were using for that. So we have I, we have list. We know that when I is 0, we've reached the end. So there's nothing more to add. So we just return a 0, right? And then otherwise, we add the value at I, and then we call the function. And so this time, we're decreasing the index, because we're going to the previous element in the list. And then we're passing in list again, because we need to keep track of that. We need to know what we're actually using to get those, to get the numbers, right? Okay, so does this make sense to everyone? Do we want to do a quick example? Let's call this function. So let's see. Actually, I don't know. Does everybody get this? Okay. Are there any questions about this? Okay. So I recommend, we could go ahead and do an example, but it's pretty simple. I think you guys can probably figure out how it works. So does anybody have any questions about this? Okay. Yeah, so it's pretty straightforward, right? So all you're doing here is just going through each time you're changing the index when you call the function, and then every time it returns from a function call, it's going to add that to your index here. And then you're going to keep adding that as you return from the function calls until you get to the top. So, all right. So, yeah, that's pretty much it for recursion. If you have any questions, please don't hesitate to ask. There are so many resources out there to help you. And pretty much if you continue taking CS classes, this is never going to go away. So you're just going to learn more and more interesting recursive problems. So it's really important to understand this, and it's really fun to think about. So, yeah. And this is going to be on the homework, so you guys should really strive to understand this. Okay, so we're done with that. We're going to go on to, hold on a sec. Okay, we're going to go on to our cloud computing lecture now.
Hello. Alright, so we're going to be teaching you guys cloud computing. My name is Osmar Coronel.
And I'm Sahil Bhatt, and we are CAs for this class and CS 398, which is Applied Cloud Computing.
So what is cloud? What is a cloud? Does anyone know? Alright, awesome. So it's not an actual cloud, but it's similar. It's this blue thing. They're both very blue and very unreachable.
What is cloud computing? Any guesses? Anyone? Connor, what is cloud computing?
Is it running applications on a distributed cloud?
Yeah,
Pretty good.
pretty good. Yeah, so in simplest terms, it's pretty much running applications on other people's computers. So using someone else's computers, that's how
So one big question about clouds is why do we need them, right? And the biggest answer is big data and big computers. Now, how big are we talking about? And also the big question, does size really matter?
It's not about the size. We all know it's not about the size. But they do tend to be really, really big. So, how big?
Basically, daily, it's 5.2 billion Google searches, 5.75 billion Facebook likes, and 656 million tweets a day.
Also, 67 million new Instagram posts, 4.3 billion Facebook messages sent, and 4 million hours of new YouTube content every day.
This all sums up to 2.5 little quintillion bytes of new data every day. Average is the same amount as 50,000 gigabytes per second. I'm sure all our computers can handle that. So, just to give you an example, if you search computer, you get lots of results. So, there's a pretty good example of big data, lots of data.
So what can we use clouds for? Cloud data storage. As we saw, there's 2.5 quintillion bytes of data produced every day, and you cannot just store that on a MacBook. You need cloud to store that. So data storage is one big use for a cloud.
Along with that, we want to process this data. All of this data in one place is a gold mine, and we want to make something out of it, find out what it's used for and how it can help us.
Machine learning, as we learned last week, machine learning is very intensive on the CPU or GPUs, and you need a lot of processing power to process those machine learning algorithms. So cloud becomes very handy when you're doing machine learning.
And along with that, we want to host our services and our software, and cloud computing allows us to do this and be able to scale up very easily.
Alright, so this is pretty much a landscape of the big data tools, platforms out there for 2017. You can see there's infrastructure, analytics, application, and just a bunch of them. They all have weird names, so we'll play a game, and the game is Big Data or Pokemon. So we'll say a name, and you guys can guess if it's a big data tool, software, or just a Pokemon.
All right,
That's
for the first one, is the first one a Pokemon? Can people raise their hands if it's a Pokemon? So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 people think this is a Pokemon. I'm guessing the rest think this is big data, or maybe something else. Let's hope it's not another banana. Splunk is a Pokemon, but don't confuse it with Splunk, which is a software suite for analyzing logs.
Flink. How many of you guys think that's a Pokemon? 1? Alright. Yeah, it's big data. It's used for stream processing. It's not a Pokemon.
Feebas. Alright, I think there are some people here who know all their Pokemons. So it is a Pokemon. Yeah, it's not a big data platform.
Impala. Pokemon or big data? Yeah, you guys are correct. It's big data. It's used for querying big data using C++.
Barbados. Big data or Pokemon? No? Big data? Alright, you guys are good. It's big data. Last one. Azure. Big data or Pokemon? Pokemon? Alright, Pokemon. You guys got us. This is a Pokemon. So the big question is, why do they all sound like Pokemons? And for those people who don't know Pokemon, why would they pick Pokemons? Anyways.
we'll talk about cloud providers now. So they're commercial companies that open up their servers so that other people can come in and use them. Google Cloud Platform, Microsoft Azure, and there's the big one, Amazon Web Services.
This image is not to scale. Amazon Web Services is actually much bigger than both of the other two. So, as I said, it's the largest by far of the public clouds. You use it every day in applications that you might not, that you probably use like without even knowing it, like Netflix, Reddit, Spotify, and millions of others.
When it goes down, half of the internet goes down. A notable example was during February 2017, where literally half of the internet went down. You cannot access Spotify, Reddit, or Netflix because Amazon servers broke down.
This is an accurate image of Amazon and working at Amazon. Coffee is not included. You have to drink from the water fountain, and you get some bananas. So why do we use a cloud provider? We want to have lots of reliability. We want to make sure that the system's always up and there's no downtime. And usually there's always someone there using in the cloud, making sure that this is working and everything's functioning the way it's supposed to. Another thing is cheap and on-demand scalability. So cloud servers work much better than downloadram.com because they give you way more RAM than the low packages that you get in downloadram.com.
Highly recommended. If you guys have not heard about it, always use download more RAM. Third one, hardware abstraction. That means that rather than companies having to build their own servers when they start up, they can just use someone else's servers, so it's a lot cheaper. A good example for that was back in 2014, NASA tried to simulate a bunch of Mars landing simulations, and they got quotations from a bunch of companies. They were like, oh, we'll build our own server to simulate the landing. And Amazon comes in and they're like, no, you can just use ours. It will be a lot cheaper. It was $1 million versus like 5,000, a lot cheaper. And the specials. So if you use Amazon Web Services, you get access to their DynamoDB, which is only for AWS. And same with Google. If you use GCP, you get access to Google Bigtable, BigQuery.
So right here we have some of the offerings from Amazon Web Services. As you guys can see, there's quite a good amount of different applications that we can use. And these are the ones from Azure, since they're number 2 in the cloud providers, so it looks like they're doing something right. And Google Cloud. So one thing that's very noticeable is that most of them have the same services, and they try and compete with each other to see who provides them the best and the cheapest. Do we have any questions? Any questions? All right, we're gonna do a little demo. So.
Alright, so what this demo is we're going to be using Kubernetes. It's software created by Google. It's open source, so you guys can use it too. It's used for scaling applications. So we're going to be using it to scale web applications to show you how Kubernetes is super useful.
So we're going to start off by running a local website. This is something that most of you might be familiar with. And we're going to be testing a specific task. So I'm going to get the website ready. All right. So when I run this website, I get the search bar over here. And basically what this search does is it finds all the number of occurrences of a word from the Black Panther Wikipedia page, and it searches through the next 10 pages that for search style. So if I look up Panther, and I press enter, or there we go, it shows me 368 occurrences, 3.79 seconds. of duration. So this website has a little cache, so we can measure how much time it takes to run something. So I'm going to clear the cache, and we're going to repeat the same process, looking at the same word, Panther, and we're going to see how long it takes for it to process 3 different people at the same time. I'm going to replicate that process by clicking the submit button 3 different times in a short amount of time. So I look up Panther, and I click it 3 times. 1, 2, 3. And this is similar to 3 people clicking and searching the same word, right, at the same time. Google has billions of users searching at the same time, and they all have to be really fast searches. As you guys can see, it went from 3 seconds to 10 seconds.
So now we'll go inside the cluster, implement Kubernetes, and you should be able to see a noticeable difference. The reason why we do this again is, so rather than waiting for your turn in the queue, you can do it simultaneously. So think of it in a way where, let's say you're trying to log into Facebook, right? And you log in, when you click login, it says, oh, your queue is, you're like the 1 million something, and then you just have to wait hours just to log in. So this will not let that happen. We also use Docker, which is a container application. What Docker pretty much is rather than creating virtual machines for each instance of your application, you create containers. Virtual machine, you can think of it as computers. So rather than buying different computers, what you do is you buy something that does your job. So it only has, let's say your computer only, or your application only needs Python, you can have a container that just with Python installed. So it doesn't cost a lot, it doesn't take up a lot of memory, just better practice. Yeah, right now we're just downloading all the dependencies from Docker. So yeah, for this application we need Python. I think it's written in Flask. So it's downloading the Flask dependencies and Kubernetes and so on. Any questions?
Cool. Alright, so right now I'm gonna create some pods. We already have the cluster set up, so it's just a matter of creating our pods, which you can relate to creating P pods, where you have different tasks in the same location, all work at the same time, and in case one of them quits or stops liking you, Kubernetes will create another one. So let's see if Kubernetes wants to create the first pods. These pods have been created such that they have replication on. So in case you want to delete a pod, it will create a new one for you. Or in case one fails, it will create a new one for you. We've also created a service, which allows us to view the URL anywhere. So anyone now has access to our website. And now we'll check out the service. So we just have to wait for it to get an IP address, and once it gets its IP address, we will have access to the website. And we will be able to compare the differences between the website locally and on Kubernetes, and find the differences between having a non-scalable website and a scalable website. All right, so we got our thing. So I'm gonna take this guy out, and I'm gonna find this guy. I'm going to put these two together. Alright, so now we have them side by side, this one being the local one and this one being the Kubernetes one. we're gonna run the same test. First running the word Panther and seeing how long it takes. So it being part of the cloud network, it runs much faster, it has much better computers than my own local computer. I'm gonna clear the cache to make sure that it doesn't take, we can measure the time again. And I'm gonna press the button 3 times simultaneously such that it replicates 3 different users using it at the same time. As you guys see, there's quite the big difference. It's still not as fast as we'd like it to be. We want it to be as fast as Google. Of course, if we want it faster, we can always create more pods, parallelize a few things, and make the whole process much faster. But otherwise, here's a clear example of why scalable Kubernetes is much better than a local computer. Questions? All right, awesome. Thank you.
That's all we have for this week. Next week we're going to be covering algorithms, and the micro lecture will be mobile development. So we'll see you next week.